So, hello and welcome to the first lecture Advanced Image Synthesis, or the first stream for the lecture Advanced Image Synthesis. My name is Jens Krüger, and I'll be giving this lecture for the most part, unless something happens to me, I should get an accident or anything. Along with me, there'll be a student teaching assistant, Andrea Ianella, and he will be responsible for the exercises. So here you can find the details of myself and Mr. Ianella. I put the room number in there, but I suppose given the current Corona situation, that is not of much interest this semester, but maybe in the future. So you got the email here. That's one way to reach us. So how else do we get in touch? Obviously via Twitch. You're most likely watching this here live on Twitch or as a video on demand stream. In addition to Twitch, we'll be using a number of other platforms such as Moodle and Jitsi Meet as platforms for this lecture. So as you can see, the lectures itself will be streamed live via Twitch, and you're welcome to post any questions, comments, or whatever in the chat. So whenever there's an issue, so maybe, I don't know, audio is not working properly, or anything, go ahead. I can see whatever you write in the chat live, and I'll respond to that. In particular, you should ask any question about the lecture itself, anything that I say, anything that's unclear. Go ahead, please write this in the chat. I've set aside enough time to talk in much detail about any question that you might have. So the lecture itself is designed so that we have a lot of time for discussion. Unfortunately, this doesn't happen as often as I would like it to. So yeah, feel free to use the chat. So that's Twitch. Obviously that's working for you, otherwise you wouldn't be watching this now. But also we have Moodle. So there's a Moodle course, just like pretty much any course. Even before we had, due to Corona, we had online courses. We were all using Moodle, and that still remains. Here you can see the Moodle ID and the login password, the Einschreibeschlüssel as it's called. So if you want to register for Moodle, I highly recommend to register for Moodle, in particular if you are a student of University Duisburg-Essen, as we'll be posting things such as exam dates or exercises or any announcements. We will post that on Moodle, so sign up for the Moodle course. Make sure you use an email address that you check often, preferably your university email address, if it doesn't get spam filtered. And also, you can download all the lecture materials from there. So once I'm done with the lecture, I'll transfer that over to YouTube. It'll also be available on Twitch for, I think, 2 weeks. But for permanent, as a permanent archive, I also transfer all the lectures over to YouTube, and there'll be a YouTube playlist which you can also access through Moodle. I mean, you can also access it through YouTube right away, but it's easier to find. Other things that we'll be providing are the lecture slides. So what you see right behind me, those slides will also be available as PDFs. So you don't need to write things such as URLs or so down. They'll also be available in the PDFs, and normally they are available before the stream. So you can, right now you could go into Moodle and download the first 2 PDFs, I think. Nonetheless, I recommend that you take notes. You can do this on printed slides or digitally or whatever you want. I recommend that you take notes, as my slides are not a script. So they're designed as slides and they're not designed as a script. That means there's a lot of information that is not on the slides, but that I talk about. Since the lecture is digital, you can of course also review the lectures themselves on YouTube or on Twitch for a while, but still I recommend that you take notes. That'll make it much easier to later remember, recapture things. Okay, so the slides are available, but that's really just a minor thing. Your notes will be the more important stuff. Okay, hi, so the chat is apparently working. Great, thanks for writing something. Okay, yeah, Twitch I already mentioned. Here it is. I recommend that you use a browser that supports low latency video playback. Here's an URL where you can check out whether your browser supports low latency playback. The problem with some browsers is that they have an added latency, which means that if you ask something in the chat, it'll appear here with, say, 10 to maybe 15 seconds delay. And that'll make a conversation just harder if it always takes me seemingly so long to get back to your questions, but this is just due to the latency. With the proper browser, latency should be around 2 to 3 seconds. So that's pretty okay. If you have any further questions, any technical issues, again, feel free to ask them either here or in the exercises. We'll do the exercises via Jitsi Meet, which is a web-based software platform for video conferencing. It's a somewhat different setup as what you see here, in that it allows face-to-face communication, which is what we want to support in an exercise-like setting. We want you to be kind of more personal and maybe feel a little bit more personal and ask maybe more or other questions than you would do here, where this is a little bit more open. Okay, so again, if you're a student at the University of Duisburg-Essen, then those exercises will be of particular interest, I suppose. And you can just click on that link here when the exercise starts, obviously, which is this week on Thursday morning. And Mr. Janella will be there to explain the first homework. Yeah, so there's homework. It's voluntary, so you don't have to do it to participate in the exam. But I highly recommend doing the homework as it's the only like real way to learn and to get to know all the things that I tell you here in greater detail. We've changed the exercises this semester a little bit, so Mr. Janella spent quite a great deal of time on updating the exercises. So we'll now be using C++ as the programming language. Just in case you've heard some of these lectures before, we moved to C++ because it's well more practical when it comes to computer graphics. It's the more standard way of doing things. If you're not familiar with C++, it shouldn't be a big deal. We'll have a somewhat short introduction to this, or at least we point you to introductory material for C++, and we will help you. Well, the exercise will start pretty slow. Okay, so we now got Moodle, we got Twitch, we got Jitsi, and on Moodle you can find the YouTube playlist for the archived Twitch streams. So any questions so far? Any organizational questions you might have? Now would be a nice place, a nice time to ask. So doesn't seem to be the case. If there are questions. No, it's not due this Thursday. I suppose you don't know the homework yet. It'll be posted on Moodle, and as far as I know, nothing has been posted yet. I'm fine. Thanks. I think the plan is that Mr. Janella will present the first assignment this Thursday, and then talk a little bit about this. But in case I'm talking nonsense here, so if he's present, go ahead and correct me. Okay, so anything else? Okay, good. Then let's start. So in case you've already watched yesterday's stream, so there'll be a couple of repetitions here. Obviously, a lot of the stuff that I already said isn't that new, and also you've seen the video already that I'm going to show. So I'll get out of the way for a second, and I just want to show you a short video about stuff that we did a couple of years ago, actually. Let me make this a little bit. So I already mentioned yesterday that video needs a little bit of an update. Hint to all of my group's members in case they are watching. But anyways, what you see here are, so those are mostly visualizations of flow fields. The video starts with flow field visualization, which is more Cyvis stuff. That's Those are approaches that I'll talk about in scientific visualization, which is every Monday, but nonetheless, it's still a graphics topic, and there's a lot of overlap of advanced image synthesis and visualization when it comes to techniques. So here's a little bit of interaction and distributed rendering with large display walls, which is also something that we've worked on. And again, it touches also a bunch of ideas that we need for that we use for advanced image synthesis, such as caustics here, volumetric effects. Talking about volumetric effects, that's a volume rendered image. Again, it's a visualization topic, a visualization of a human body, obviously, but similar effects are also a part of this lecture here. We'll take more of a, well, gaming approach maybe, or effects approach to volumetric effects, but whether you use them for clouds or for dust, smoke, or in this case, organs for humans is technologically wise pretty much the same. So here, for instance, you can see a visualization of fluid mixing simulation. Those are two fluids. One is visible, the other one's hidden in this simulation. That would be on top, and one fluid is moving upwards into the second invisible fluid, and you see vortices forming. And again, it's a volumetric effect. This could also be smoke. Smoke is also a fluid. Fluid is not the same as a liquid. As a matter of fact, a liquid is a fluid, but smoke as well, and plasma. So here is another visualization. Again, it's a fuzzy thing. It's a volumetric object. Again, a human. Yeah, so this is a flow visualization. It's in particular a segmentation. So taking a flow, a wind, or moving water, a magnetic field, electrical field, any type of vector field. And the purpose here of that approach was to automatically separate parts of the field that have similar behavior or that belong together. Okay, here's a typical topic that we'll also talk in advanced image synthesis. That's terrain rendering, in particular large-scale terrain rendering. We're talking here about terabytes of data that comprise a high-resolution terrain that you want to interactively explore when we think about visualization, or that you want to, I don't know, fly over with a plane, or walk through in a game and, I don't know, kill everything that moves, or whatever you do in the game. Okay, so that's pretty much the end of the video. It's again volume visualization, and then the key point here of that section is that most of the stuff that we do here is tuned so that it also works on small-scale devices, such as telephones or tablets. Okay, so that's pretty much it for the video. Now let's just briefly figure out or explain. Let me just briefly explain how this this particular lecture, Advanced Image Synthesis, fits into our whole curriculum. We do in the winter, I do computer graphics, the lecture Computer Graphics, which is kind of the introductory course to, well, computer graphics. And Advanced Image Synthesis, on the other hand, is kind of like computer graphics too. So the normal idea, or the initial idea, was that you first attend computer graphics and then you attend advanced image synthesis. However, for some reason, as it turned out in the last couple of years, surprisingly, most students actually attend advanced image synthesis first and then computer graphics. I think that has something to do with the way your semesters are structured. It's not ideal, but it's no big deal either. So I've adjusted the lectures to compensate for that. So we'll do a lot of repetitive stuff, in particular today and the rest of the week. I'll repeat pretty much slide by slide the rasterization part of computer graphics. So if you're doing it the right way, that will be pretty boring, I suppose, or it will be a nice refresher, depending how you think about it. So it's no big deal if you do this the other way around, but it wasn't initially meant to be that way. Anyways, we have advanced image synthesis this semester and scientific visualization along with that. So if you want to, feel free to also watch the scientific vis lectures. We also teach Grundlegende Programmiertechniken. It's a bachelor class, but I suppose for most of you at least attending the master, that is no big deal. It already happened. We usually have master's and bachelor projects, none this semester though, but we have a seminar. So if you're looking for a seminar as well, so we have a seminar. Kickoff meeting is this Thursday, and it's also via Jitsi. If you want to know a few details about the seminar, it's about how to give an engaging computer science speech. It's the details can be found on our teaching webpage, just like the details to a lot of other stuff regarding the lectures that I just mentioned. One last remark, or the second to last remark actually, is about the exam at the end of the semester. With just like with all master's classes, we do oral exams, most likely not in presence, but I don't know yet what's going to happen. Normally we do them in presence at our offices. However, due to the current situation with the pandemic, we did the oral exam the last 2 semesters as I think Skype conference called. Worked out pretty well, but I prefer the personal communication, but not in the middle of a pandemic. So my guess is that they'll be via Skype again. But nonetheless, pretty much the same thing, 30 to 45 minutes in presence or remotely. But it's still a way to go till we get to the exams. One other word about the exercises. I said the exercises are kind of 2 things: homework that you can do if you want to, and the meetings. The homework is bi-weekly, so every other week you'll get a new assignment that you can and should work on as kind of a additional motivational kick. We've got this setup that if you get more than 80% of the score, we score the assignments, which is mostly for you to judge your own abilities, but we keep track of the scores, and if you get more than 80% of the scores at this threshold, we'll give you kind of 1 free question in the oral exam. So if there's one question that you don't want to answer because you supposedly think your answer would not be accurate, you can say, well, I want to talk about a different topic. However, as it turns out, once you get beyond these 80%, you don't need that, which is kind of the secret idea. But anyways, we keep track of that. Okay, so that's pretty much it in terms of introduction. Any questions about this? Any questions about, I don't know, lecture, exam, exercises, homework, anything? Okay, well, you're not even a student, at least not here. So, but you get a lot of channel points, I suppose, for attending pretty much anything. Okay, good. And you get my gratitude for making sure that I'm aware that the chat is still working. Good. So then let's get started. As I said, it's not computer graphics, it's advanced image synthesis, but nonetheless, let me quickly give you an idea of my definition of computer graphics. Why do I stress this "my" so much? The reason is that this term isn't like super clearly defined. So pretty much everyone has a slightly and sometimes significantly different understanding of computer graphics. And this varies from art, the graphics design, pretty much mathematical theories, and so on and so forth. So this is why I want to give you my idea here. So I would put the following subtopics as underneath computer graphics. One is rendering, okay? The other one's animation, imaging, computer vision, and modeling. So those are 4 subcategories that I would say are all belong into the area of computer graphics. Okay, and now let's quickly look at those subtopics. So what do I mean by rendering? And I just want to give you a very short definition. Rendering is literally the display of images, okay, or the display of scenes, or just coloring pixels. And since it's on a computer, we do this on a computer, this all happens on a computer system. Okay, so that's the rendering part. But this is not all, right? So computer graphics is more. It also encapsulates, at least in my definition, also includes animation and simulation. And the difference between animation and simulation, it's really, really fluent, or the line between the two, right? So today, in most cases, it's actually more a continuum. Okay, but what is this? Well, it's getting things into motion, right? It's the generation and the representation of dynamic imagery on a computer. Okay, what does it take to do dynamic imagery? Well, it takes some sort of a model or representation or idea or concept of how things are supposed to move. Okay, so then there's a whole different area, which is kind of the opposite direction of what I said before, and that's imaging and computer vision. Okay, where rendering is taking data and turning into pixel values, imaging and computer vision is taking pixel values and turning into data. Okay, and I agree, data is a very general term. Pixel values are also data, but I guess you get the basic idea, right? Turning it into knowledge. So that is imaging and computer vision. And then the final thing that I put on the previous slide with the 4 sections is modeling. Like, modeling is this idea of how do I represent something in a computer system? It should be effective, it should work, it should do what it's supposed to do, and it should do this efficiently. Okay, effective and efficiently, 2 important things. In particular, geometric shapes. Okay, so we want an efficient and effective representation, or better, effective and efficient, let's put it this way, representation of a geometric shape on a computer. Okay, so that is basically what modeling is about. And you can already see that there's a lot of interplay, right? So in the modeling stage, you might want to consider the animation right away to build that into your data structure so that it's able to change from one shape into another, for example. Okay. And then something that I haven't put on purpose on the previous slide is visualization. Okay, visualization can also be considered a sub part of computer graphics. Okay, surprisingly, that's probably the most disputed definition here, whether computer graphics is visualization or whether visualization is computer graphics. Okay, so which one is a sub set of the other? So here I put visualization as sort of a subcategory underneath computer graphics, but as I already said, I have a whole lecture on that one. Okay, so that's again the definition. Now let's look at what will this particular stream, not today, but over the next couple of weeks and months, what will this be about? We can basically break this down into a few parts. So the first part will be about interactive image synthesis. Okay, so how can we make things super fast so that they would work on a commodity PC, on a cell phone, maybe on a smartwatch, on something that is, compared to a supercomputer, today's supercomputers at least, relatively slow. But nonetheless, we want to design something that is fast enough so that it works very fast with hundreds of updates per second. Okay, we'll use OpenGL for that. I'll also make some references to DirectX, but we'll mostly be using a rasterization API for that. And we've also used rasterization APIs in computer graphics. But here I want to talk about effects that are well, not an inherent feature of the graphics APIs, such as reflections, refractions, and shadows. Those are things that require some global knowledge, right? So for instance, if you do a shadow here, right? I mean, it takes at least 2 things, right? The shadow at the floor requires, well, the floor, obviously, plus knowledge of the tree. And then you need to figure out where's the tree blocking the light source so that it casts a shadow on the floor. And that is something that we call indirect or global. And in case you've already attended computer graphics, you know that, well, in a rasterization API, you don't have global knowledge. So how do we still make this work? And the same is true for reflection. Okay, every point needs to potentially know the environment, and the same also is true for refraction. So that will be part 1, where we look at effects. Okay, here also volumetric effects per hair, fur will be one thing, particle systems will be another thing. And then I also want to touch on a topic that is also a repetition from computer graphics. Those are high-level APIs. So I also want to review the high-level APIs a little bit. Okay, so that's all going to be part one. Okay, interactive graphics, effects, and making that pass so that it works in a game, virtual environment, I don't know, virtual reality, augmented reality, so things such as this. So part two will be about physics-based rendering. That doesn't necessarily mean that it's going to be slow. We can also do physics-based rendering with the goal in mind to do this interactively with hundreds of updates per second. But we'll just approach graphics a little bit different. Okay, so we'll take a step back when in the first part, it was all about, okay, how can we do things fast? Okay, and they don't necessarily have to be correct. They just have to look correct. Okay, for the physics-based rendering part, we'll kind of take a step back and look. Okay, what's at least correct considering a reasonable model? Okay, I mean, what is correct anyways if we talk about reality? But we want to use a physical model, physics-based model, and then from that one figure out, okay, how does light interact with the scene, for instance? Yeah, and then once we figure that out, we'll check, okay, how much can we make this relatively complex, in particular numerically complex and time-consuming task? How can we speed this up so that it doesn't take weeks or hours to compute an image, but maybe just minutes or maybe just milliseconds, so that we can reuse that for again for interactive graphics. How much do we miss when we want to make things fast? Okay, but the approach is a little bit different in that we kind of know what's right, or what at least follows a physical model, and then we get a better idea what will be missing. Okay, so here are a couple of examples. Those are, for instance, pre-computed radiance transfer images, and that'll be part two. Part three will be about any other business, just like in a meeting. So other topics that don't really fit part one or part two, but are important in computer graphics as well. And it depends a little bit on how quick we are, what I'll get done in part three. So one thing that I want to talk about is HDR, high dynamic range imaging. It's not a big deal, but it's a pretty interesting topic, and it's a pretty important topic when you do computer graphics. So here are a few HDR images. Other things are point-based rendering. So I'll, in a bit, explain that most graphic approaches, at least interactive graphic approaches, are based on meshes of polygons, usually triangles. But under certain conditions, we might want to use points as primitives. They do have a bunch of advantages, also a few drawbacks. So that's point-based graphics. And then, as you've seen in the video before, I also want to look at other specific situations, such as terrains. Fur was also such an example that I've already had on a slide. Of course, you can render a terrain, or you can render fur. You can just render that as if it would be any other object, right? If I have a general concept, which I'll introduce soon, to model surfaces, I can of course model a terrain. I can model a valley, or I can model a mountain, just like I would model anything else. The idea, however, is that since terrains are something that we encounter fairly often in a virtual environment, there's usually something to stand on, unless you have a space flying game or something, or a space flying environment. But even then, there's still planets around usually. So it's a thing that happens fairly often, just like fur, right? Pretty much everything is furry or hairy in some way or another. Right? Anything that's hued usually has got fur on it. And since both of these things are kind of features that we often want, it makes sense to look at them separately and see, okay, can we just maybe give them special treatment to be faster, or qualitatively wise better? Okay, and that's the idea with the terrain and the fur, for instance. So, and then I want to talk about a few other things, namely, like, what does the industry use? Okay, so in particular, I want to look at the RAISE approach, which is the underlying rendering algorithm that RenderMan uses, which is a software by ILM, Industrial Light and Magic, and for instance, it's been used to do these movies here, as well as parts of Avatar. Most of that wasn't done by ILM, but by Veta, if I recall correctly. But in any case, I want to talk about what is used in production, and I promise there'll be a few surprises. Okay. So one of the interesting concepts that will pop up in this lecture a lot are this sort of this idea of, on one hand, interactivity. You want to make things fast, very fast, so that they're interactive, that when I interact with the system, that it reacts so quickly that I can feel a causality. So I flip a switch and something happens immediately, or I move my arm and the flip switches. That's one side. And then the other side is photorealism, right? I want to get things to look just like in reality. And often these two concepts contradict each other, right? The more real you get something, the more work it might be, and the longer it takes, and the less interactive it becomes. Okay, and there's different situations where one is more important than the other. So, for instance, if you are in a virtual reality setup, so you're wearing, I don't know, a headset and you're walking around, then interactivity is kind of the most important thing. If something isn't interactive, it doesn't matter how realistic it looks, you're still going to throw up because you get motion sick. Okay. So here are a couple of other examples of computer-generated images that look relatively real. Okay, we'll look at what does it take. Okay, so two final slides on prerequisites. The first one is here, and that is one of my very few slides with a lot of bullet points, basically just to discourage you to use them. But nonetheless, what are helpful prerequisites? And those are things, and I'm not going to read this, you can all read yourself, right? But basically, the more you know about graphics, the better. Okay, if you've attended computer graphics before, and I mentioned that a few minutes ago, it's great because that's how it meant to be. That is how it was meant to be. However, if you don't know this, and I also mentioned that, I'm aware of the fact that a lot of people do this, a lot of students do this in wrong order, and I adjusted the lecture accordingly. So it's a helpful prerequisite, not a necessity. Yeah? So that's kind of important here. And since the last semester was also digital only, you can, if you want to review the entire computer graphics stream. It's available on YouTube. So go ahead and watch that. Yeah, you know, since you talk about reading, still the library is your friend, okay? At least when it's open. I think it's open right now. So the university library is open as far as I know. At least you can pick up books. We've ordered a couple of books on the webpage. There's a list of books that, if you're interested in them, that would fit the lecture nicely, that would fit the stream nicely. But I'll generally explain everything that's necessary to go through the exam. And in particular, if you participate in the exercises, do the homework, there's really no reason to look at a book unless you're interested in some of the techniques that I present here in more detail. Then it's a potentially good idea. But if you're interested in some details, I can point you specifically to where you should look. Okay, so now what's next? Let's get started. Okay, so we're about half an hour in the lecture, and I haven't really said much about computer graphics, except that I've defined a few terms and told you what I'm going to talk about. So as promised, I'll start with a repetition of the Rasterization API. And literally 99% of the slides that I'll present now are just verbatim from computer graphics. So and if you attend computer graphics, hopefully this will all sound familiar. If not, even better. Well, or not, I don't know. In any case, let's get started. So let's first start with this two worlds collide situation here. I want to start with that because there are these two notions, low-level API and a high-level API. Okay, so what does that mean? It actually gets even more complicated these days because we have now low-level APIs, such as Vulkan or Metal. Those would be probably considered low-level APIs, or DirectX 12. But basically, this is stuff like OpenGL, DirectX, pre-12, I guess, and high-level APIs are things that I talk in more detail later on. So those would be scene graph APIs, for instance. The idea of a low-level API is you get very low-level control over how to render an image, and this is normally blazing fast. However, it's incredibly hard to learn. In particular, it's got a very, very steep learning curve. What does that mean? Well, it means if you have no experience in rasterization computer graphics APIs, you're good. It's fine. You're watching the right stream. But you have to experience some of those. You have to experience the API yourself. You have to use the API. You have to code to really get to know what's going on. Okay, and the trouble here is that if you start with a new programming language, right? You learn a new programming language. You start with a Hello World example, right? And depending on your language, your Hello World is maybe, I don't know, two to, I don't know, probably 10 lines, right? If you take an overkill syntax language like Java, it's maybe 10 lines or 8 lines that it takes to get the thing to say Hello World. If you use Python, it's 1 line. But this can be easily explained, okay? Now here's the thing. If you want to render the simplest thing, which is about a triangle, in say OpenGL, and you would do this from scratch, it would take you roughly 1,500 lines of code, I would suppose. And any of those lines, if it's wrong, there's a pretty good chance you're not seeing anything, okay? And that is a catastrophe for learning, okay? So what is the consequence of that one? The consequence is there's only very few people around that know how to use low-level graphics APIs properly. There's apparently one who's not even able to pronounce it properly. So anyways, so there's only very few people around, and that has a couple of consequences in turn. One is a lot of the examples that you will find on the internet are broken. A lot of the comments that you find in forums are incorrect. A lot of the source code that you can download from tutorials has bugs. So that's like one. So be aware that if you copy code from the web, there's a pretty high chance it's incorrect. That doesn't mean it doesn't get the job done, but just to give you an example, you copy code that renders a single triangle, okay? And if at one point you added the second triangle, it should render 2 triangles, but it's very likely that it doesn't render anything because there's a mistake somewhere along the way and it just coincidentally renders that 1 triangle to start with. So that's the first thing to know, okay? And the second thing, so that's probably bad. The second thing is good. If you learn how to do this, right, you are part of that small group of folks that know how to do this, and you'll make a ton of money when you work for a company. So that's the good part about it. So bear with me. It's actually a nice thing. So those are the low-level APIs, and maybe it's not as bad as I'll make this sound here, but nonetheless, I know from my own experience that starting with the graphics programming can be pretty frustrating, and that's why we have the exercises. So if you work on this for hours and you still don't see the damn triangle, we can help you figure out what's going wrong. And debugging tools have improved a little bit. So what is this whole graphics low-level pipeline? What does this look like? It looks like an ogre. No, let's just say I want to render this ogre here, this Shrek guy. So what's the first thing you have to do? Well, the first thing is you have to somehow represent this in your computer. Okay, so here's a small image of a mesh. What is a mesh? A mesh is pretty much a set of things. And what are these things here? In this case, those are polygons. Okay, so quadrilaterals, triangles, all kinds of polygons you can use depending on how many edges or vertices these polygons have. What we will be using for the most part is just a triangle mesh. Okay, so we'll just break down your representation into a set of triangles. Okay, so that seems to be pretty straightforward. If, for instance, I have a quadrilateral, which is just a polygon with 4 vertices, I can just cut this into 2 triangles, you're good to go. We'll later on see that this actually isn't as trivial as one might think. Well, I mean, it's at first pretty trivial, but it has certain consequences that you'll later see. But nonetheless, let's just assume we can break everything down into triangles, which is true. What is a triangle anyway? A triangle is, well, it's 3 vertices. Here you go. Okay, it's 3 vertices, and then maybe a little bit of information that says, well, these 3 vertices are one triangle. So that's pretty much what a triangle is. And when we kind of go back to this idea of that we ultimately want to render this guy here, what we have is a set of these thingies, right? So we have a potentially gigantic set, like millions and millions of these triangles or vertices, and they make up the original idea of Shrek, okay? So what we basically, excuse me, what we basically end up with is a stream of these triangles, right? A ton of these triangles are like in a stream, and all of them together make up the object. And we call this a vertex stream, okay? I don't call this triangle stream because we process these triangles vertex by vertex. And this is why we consider this a vertex stream, okay? It's just a seemingly endless stream of vertices. And then this is traditionally, I'm talking about 9099 here something, or 90 something. This is traditionally run through a so-called transform and lighting engine. TNL, if you're old enough, you probably remember there were things called TNL graphics cards around transform and lighting. It's still very important today, yeah? So bear with me here. So if I give you some history lesson here, it's always not just to make sure that you know that I am older than you. It always serves a certain purpose. When I give you a history lesson, the purpose is usually to show you how much that concept, which might be 30 years old, is still very important today, and you need to know it, otherwise you can't do any of the newer stuff. So what's the result of transform and lighting? If we look at this from a syntax point of view, right? We started with Shrek, then we turned this into a stream of vertices. What do we get once we've transformed each and every vertex separately through the stream? Well, we get a set of transformed vertices, literally transformed and lit vertices, okay? So no big deal here. And generally they are transformed in a way so that they're now on screen. So this is why I put a white piece of paper behind that, so it's sort of flat now. And then this stream of these transformed and lit vertices is run through a piece of hardware that's called the rasterizer. Hence, this whole thing is called rasterization. We need to be a little bit careful. This term is overloaded, right? This thing is called rasterizer, and the entire pipeline that I say here is often referred to as a rasterizer, right? So you always need to know which one's the right rasterizer at the moment I talk about this. So what's the purpose of that thing and what's its output? Well, its input are the vertices, this vertex stream. They are at that point, when they get rasterized, they are reconnected to triangles. Okay, so inside the rasterizer, you look at each triangle as an entity, and what it outputs is it figures out for each triangle, where is this on my screen? Okay, where's this triangle located on screen? And then it checks, okay, which pixels on screen overlap with this triangle. And then it generates a new stream. It generates a stream of all of those little pixels that overlap with the triangle. And we call those things fragments. Okay, what's the difference between a fragment and a pixel? Pixel is the thing on screen. Fragment is the thing that wants to be written onto a pixel. Okay, it's a data entity, just like a vertex. A fragment is a piece of data, or it's a set of information that you process further. The pipeline isn't done yet, and then ultimately they might end up changing the values of pixels. Okay, so that's the difference. So for our example here, the single triangle, we now have a stream. So for each triangle, we potentially produce thousands of fragments, and then for all triangles together, we have a large stream of those fragments, and that is further processed in the fragment stage. Fragment stream, fragment stage processing. And I've depicted this here as, well, this grid here, so you now see that this triangle is supposed to overlap this area. Notice how I color them slightly different, right? This is because the rasterizer not only figures out where are they located, but also what their values are. So it does a concept that's called shading. So it fills the interior of every polygon, at least when I tell it to do it. It fills the interior, and that means it interpolates the value. More about interpolation later on. Then traditionally, again, fixed function pipeline comes a process that's called texturing. So a texture is applied to the object. I'll talk about textures in a lot of detail. If you attended computer graphics, you know I make a big fuss about textures, in particular about not considering them images that we stick to the surface. So I'll probably not say much at this point here. Do not complicate things. But after that, you have a more you have more flexibility with textures. Let's put it like this for now, to modify the surface behavior, right? In particular, it can be non-linear behavior. So it's not just a linear gradient over your object, but it might be pretty much anything, whatever you put in your texture. And then ultimately, the pipeline decides which of those fragments now survives a bunch of tests and operations, and potentially gets modified by something that we call blending. And then it's, voila, written into the frame buffer, and we ultimately call it a pixel value. Or if it fails any of these tests, it's discarded, and the whole stuff that you've done before, you did all for nothing, which isn't super efficient, but that's the way how it works. Okay, so ultimately it's written out. So if we take this entire thing here and want to classify this, we can classify this into 3 stages. Basically, the first one is, well, stuff that you got to do. You have to figure out what you want to do, and you've got to break this down into a computer generated or a computer friendly representation, maybe with the aid of some sort of software. And then the driver kicks in and processes that. And the next step will be the geometry processing. So the next thing will be to process, well, each of those geometric primitives, the vertices, on its own, reassemble them into a triangle, rasterize them, and then we do pixel or fragment processing. So DirectX calls this pixel processing, OpenGL calls it fragment processing. I personally would say fragment processing is the better description, but well, folks never really figured out how to call this, so I put both on. Okay, just so that you know that there's again 2 ways how to describe this part of the pipeline. But ultimately, you get values out of it. What values? Color values usually. Pixels on screen are generally color values. So how does that happen? So now I gave you a brief overview of a somewhat dated pipeline. How does this happen? And there's a lot of things going on. So I put just a bunch of keywords here. In the center, I put graphics APIs. Because while you can do all of this in software, so you can implement this pipeline just as a piece of software, the reason why it's so popular, the reason why it's so efficient, and why this is the pipeline that drives games, interactive environments, is it's designed in a way, the pipeline is designed in a way that it's relatively easy to build cheap high-performance hardware that performs most of these operations, if not all of them, on a dedicated processor, which we call GPU these days, graphics processing unit. Okay, and they come in these shapes and forms, right? Graphics cards. Okay, so since you don't want to program hardware directly, that's a pain. You generally interface with this external piece of hardware. External meaning it's not your CPU environment. You communicate with this external piece of hardware through some API, and that's exactly what OpenGL, what DirectX, what Metal, what Vulkan does for you. And there's different levels of abstractions here. Okay, so that's the basic idea. So this is why I want to talk about the graphics API now, because well, this is how we generally use this. And this is very different from how I talked about, say, a ray tracing approach in computer graphics, and how I'll talk about something such as radiosity, for instance, here. In these cases, we would actually write everything ourselves. We would write the code all ourselves and then run it. Here, we also write a lot of code, but that code just controls hardware, okay? I mean, technically, the other code also controls your CPU, but I guess you know what I mean. So let's do a little bit of a history lesson, right? A long time in a galaxy far away, graphics cards looked like this. So this is one of the first graphics cards that I happen to own. And what is interesting about old school hardware is that today's hardware, even though it's significantly advanced, it's multiple orders of magnitude faster, it still, at least on the API level, shares a lot of concepts. Okay, So hardware has advanced and advanced, but the APIs haven't really that much advanced. So OpenGL 1.0 and OpenGL 4.0 or 4.5 or 6 or 7, where we are, 4.7, I think. I can't remember what the current is. But anyways, they still have a lot of similarities. Okay, and if you run them in compatibility, even OpenGL 1.0 code still works in OpenGL 4.7. So, and this is why this is nice, because today's APIs kind of follow a lot of the paradigms of this hardware. And since it's old hardware, we can see a lot of things better. So for instance, you can see the memory, right? You can still see this in modern cards if they're not all in one place. But you can see there's two processors here. They're both the same, so you have parallelization going on. And that's kind of a key concept. That is the key concept in rasterization, that the idea, yeah, it's a 3DFX, yeah. The idea is that the rasterization pipeline is designed in a way that it's trivially parallelizable. It runs extremely well in parallel, and so if you have 1,000 processors, you get 1,000 times speed up. And that's really the cool idea about rasterization, which is not true for a lot of other things. Okay, so that's the 3DFX. While that was the card that I was able to afford as a student, this is a piece of hardware of about the same period in time that I certainly was not able to afford. This is, if I recall correctly, it's an infinite reality. It's an SGI machine. And this one's even cooler in terms of seeing the hardware. If you have the chance to look at one of those at the museum or get one on eBay. I've always considered getting one on eBay. They're actually pretty cheap these days, but they consume so much space. I wouldn't know where to put them. But the cool thing is, if you open one of the cabinets, you can actually see there's boards that say frame buffer, depth buffer. So you can literally look at the depth buffer and kind of look at these groups of pixels. You can see them as little chips. So and OpenGL was designed for this. As a matter of fact, OpenGL was designed by a company called SGI, who also happened to make these machines here. And they came up with an idea called the fixed function pipeline. They didn't call it this way back in the days, but once we got a programmable function pipeline, people started calling this part a fixed function pipeline. So again, a side note, I guess today no one would use a fixed function pipeline really. And with the latest APIs, if you don't run them in compatibility mode, you can't even use the fixed function pipeline. But here's the thing. What you do when you use what's called programmable pipeline, where you can control the pipeline, 99% of the time what you do is you control them in a way that it does exactly the same as the fixed function pipeline, plus your 1% change. Okay, so you have to know the 99% before you can add the 1%. So it actually got more complicated with the programmable function pipeline, because now you have to replicate something that was done previously for you. And this is why it's important to know how things work in a fixed function environment so you can replicate that functionality. Okay, so this is actually the same as kind of the Shrek example from before, at least parts of it, but in more detail. Okay, so we again start with geometry, and then we do geometry processing, do rasterization here, which I called scan conversion, which is yet another term for the same idea. I just want to show you all the different terminologies here. And then we do the fragment processing, and ultimately right into the frame buffer. And I want to start, that's why it's red, with the geometry. How do we get this thing started? How do we fire up this pipeline? Okay, and yeah, we could do this with OpenGL. And so I want to start, there are multiple versions of OpenGL. They all build on top of each other. I want to start with something like pre-OpenGL 3.0. It doesn't really matter why it's pre-OpenGL 3.0, but this is the way how you did things before OpenGL 3.0 came out, which is a few decades ago. But again, just bear with me for a second so that I can get you the basic concept across, and that is that a rendering pipeline, a graphics API, works on something that's called a state machine. And that is both super efficient and a pain in the neck to work with. Okay, and I guess these two things always, or most of the time, come in pairs. Every time something is super efficient, it's no fun to work with. And that's probably, or certainly true for a graphic state machine. So what do I mean by state machine? I mean that you can imagine OpenGL being just a huge switchboard with a ton of switches that you can either turn on or off, or maybe like rotational dials where you can set a few different stages. Okay, and that's literally it. So if you look at the code here, so that's actual C code or C plus. Well, it's C code really. So OpenGL is a C API. You can of course also use it in C++, but this here is would work straight in C. So and I colored. I used 3 different colors here. So green is for comments. Yellow is for state changes. Every time I flip one of those switches, that's yellow. And everything that's not yellow, which are just these 3 calls here, those are things that for once don't really change the state of the state machine. So you see that the majority of the code does state changes. And what's so bad about a state change? Or let's first just look at this code, what it does. Well, it's just a piece of the code that it would take a lot of code around this to get this to work. But the basic idea is that I say I want to get smooth shading, which is also referred to as grow shading, more on that later. I want lighting to be enabled, and just for the fun of it, I also put this here as comments. And then I want to render triangles, whereas that means in this case a single triangle. I want to render a single triangle, so I say, okay, now here come triangles. Here comes a triangle. Which is made up of 3 vertices that have the coordinates t1, t2, and t3, and those are arrays that I defined previously. The first vertex has a certain color and a normal, whatever a normal is, it's just a parameter for now. The second one has a color, and the third one apparently doesn't have a color because I don't set it. And then I'm done. So go. So GLN basically means go, render. Okay, so that's the go order. That's the basic idea here, okay? So, but now for the fun part, now for the state machine fun part. What's fun or not, I'm being here sarcastic, by the way. What's not so funny in terms of understanding this is any state that I set remains set until I change it. Depending on your driver, sometimes even when you close the program and reopen it, but I guess that's a bug. But at least as long as my program runs, it's a well-defined behavior. If I change a state, this state remains this way. Okay, so let's just look at this very simple example here, what this means for our 3 vertices. That means the first vertex has color C1, whatever that is. Let's say C1 is red. It has a certain normal, and it has a position. So the second vertex at position T2 has color C2, normal N1, and position T2. Why does it have N1? Because I haven't changed it. I said, okay, whatever comes now has normal N1. And since I've never touched that after this point, this one gets the same normal. So what's with the third vertex? Well, it has color C2 and normal N1 because I've neither changed the color after this line here nor the normal. So the idea of this concept is that it's very efficient in terms I need fewer calls, because if something doesn't change, I don't need to touch it, but it makes it very hard to read. Now, to make these things even funnier or even harder, say that I want to use a fairly modern concept called object-oriented programming, at least fairly new to OpenGL, and I put this into a class, right? I put this into a class, I put this into my rendering, a game, into the rendering part of my game, and I render this triangle here. Now, let's say that's a cloud, okay? And then somewhere else in my code, I render a plane which is supposed to fly through the cloud, okay? So somewhere else in my code, I also have some code that sends triangles. Now, if in my other piece of code, which maybe gets called 5 minutes later, okay, assuming that there's no rendering going on in between, and I just send a vertex, it'll still have color C2 and normal N1 because I haven't touched that, I haven't changed that, okay? So, and this is really what makes graphics programming so hard, because you need a lot of concentration. It's hard to debug because everything is global, okay? Each and every graphics routine writes to literally a single global variable. OpenGL is implemented as a global variable that's available everywhere. That makes it impossible to decouple one part of your code from another. You can do whatever you want. There's no way, in no efficient way at least, how to not at least consider possible interactions. Okay, and that's what makes it hard to make scalability hard when it comes to writing code. So it requires a lot of concentration. You have to keep this in mind. Like, how do I really have to set the normal here? Is there any other piece in my code that potentially changes the normal? If the answer is no, cool. Don't send the normals. Save time. Get a faster game. If 10 years later, some other developer adds code somewhere else and changes the normal there, your code will break. Okay, which is not cool. But that's how it works. Okay, so hopefully I scared you enough. It's still doable. So let's look at this GL triangle thing, which was obviously a constant. You've probably gathered by now that everything that is OpenGL specific starts with GL. Let's just go one slide back. So lowercase gl is for all function names. They all start with a lowercase gl. And constants are, and they use camel case, and constant use uppercase with underscore, but they also start with gl. Okay. So apart from GL triangles, there's also points, lines, line strips. So there's a couple of things. But as it turns out, pretty much everything is triangles these days. It's not necessarily GL triangles, and might also be a GL triangle strip or so. Details might differ from driver to driver and graphics card to graphics card. But essentially everything is broken down into triangles. That's an idea in OpenGL. So if you render a line, it's a thin triangle. If you render a point, it's a tiny triangle. If you render a quadrilateral, it'll be broken down into two triangles. You get the idea. Okay, so while you can do this, at least with pre-OpenGL 4.0, 3.0 APIs, it's generally broken down into triangles, which means you might as well use triangles to start with. So that's the basic idea. Now, how do we specify geometry? Yeah. Act 1, immediate mode. So there's different modes, there's different ways how to get this geometry thing started. And I haven't even talked about the rest of the pipeline, right? I'm just talking about how to get this thing started. Okay. So I apparently say GL begin, and the indentation here is just me trying to make this code somehow readable, but it's really just a state. I can do GL begin, GL triangles, and then somewhere else in my code, I can call GL vertex or GL end, right? They don't even have to be collocated in code or in time. It's just that as soon as I call GL end, and hopefully I call GL begin before, otherwise I get undefined behavior. As soon as I call GL end, things are set in motion, okay? So here you can see me rendering or sending two triangles. How do I know this? Well, I say triangles. Every triangle has 3 vertices. I send 6 vertices. I expect 2 triangles. What happens if I send 5 vertices? I get 1 triangle. What happens if I send 4? I get 1 triangle. That's not even an error. That's just that's if it's less than a multiple of 3, the last part is ignored. Okay. What you notice here is let's look at the vertex calls here. So they all start with GL, so you can just ignore that part, right? It's a GL call. Then comes vertex. Apparently we want to send a vertex. Okay, I guess that's clear. It's a vertex. Okay, we had GL normal, we had GL color before. And then it starts to get a little bit fuzzy. We have a 3, and then we have an F, and we have a V. Okay, so what is that good for? And you got to know one thing about OpenGL. It's a C API. And it's a pretty old C API. And one of the ideas is that it should be backward compatible. So even today, it doesn't use the concept of overloading methods. So every method that has different parameters, even if it does the same stuff, needs to be called different. Okay? So this is why we have a GL vertex 3F. What does it mean? It means, well, I'll send you 3 floating point values, and you please use that as your vertex coordinates. There's also GL vertex 3D, which means I sent you 3 double coordinates. The D stands for double, not for 3-dimensional or so, right? There's also a 4F, by the way. Later more why we need 4-dimensional coordinates, or a 2D, or a 2I, or a 1I. I sent you 1 coordinate, so you have to make up Y and Z yourself, and that's going to be an integer. Okay, so there's a ton of different GL vertex. To make things a little bit more complex or more efficient, you can also add a V to your call. So there's a GL vertex 3FV. What does that mean? It means, okay, I'll send you 3 floating point values, but as a pointer to a vector or a pointer to a memory location where hopefully you dumped at least 3 floats, because I, being OpenGL, I'm going to read 3 floats from that location no matter what happens. And if I crash your memory, it's fine. It's your fault. Okay, so this is how this works. And here's a couple of examples. Okay, so one of the things that drove me mad a few decades ago when I started to write OpenGL code, I read tutorials about this and a few books, and I saw this notation here. Okay, so I saw this notation here. You can call GL vertex star, And so I wrote down GL vertex star, and it didn't work. And it kind of drove me nuts until 10 pages further, it was like, oh yeah, star means, okay, you can put in this and this and this and this. Okay, great. Why didn't you tell me from the start? So whenever I write GL vertex star, and don't worry, I'm not going to do many OpenGL examples here beyond this very first introductory course, because it's really something that you have to use yourself. Otherwise, you just get frustrated from me bragging about how much of a pain this is. But it's doable, okay? So just a side note, it's doable, you can learn this. So GL vertex star means the star, this is going to be this 3F, 3D, 4D, 40F, okay? And I've collected a few examples here at the bottom. When there's no star, it means there's only one call. GL color is easy. It's always 4 parameters. They always float, okay? So, but you can really, it sometimes gets really funny. So here, GL vertex attribute 4BNSUV. So just as a side note, that means I want to specify vertex attribute in 4-dimensional, non-normalized, unsigned short vertex notation. Okay, so these things can be really long, and fortunately, that's the good news. Okay, so here's for a change good news about OpenGL is you hardly ever need so many calls. And the first thing you do, or the second thing, once you've got your one triangle code, is you throw all of that into your own class library, or you use classes that someone else designed, and then you never see those OpenGL calls. So when you write OpenGL, even if you write OpenGL code, after a relatively short period of time, you won't see the OpenGL calls that much. So you use some sort of abstraction layer. But as I said, since everything is global, you have to still be aware that this is around, because your abstraction layer can't really abstract very well. You have to be aware that if I make this call after that call, there's some states being set here that might mess with that stuff. Okay, so while in most examples you won't, after a while, don't see the calls that much, you still have to know that they're there. Okay, and which ones are there. Good. So much for the fun. So let's talk about the second way to specify geometry. I said there's multiple ways. Now we got Act 2. So let me just go back a few slides. So here was the first way. Okay, here I send 2 triangles and each vertex on their own. So this approach, while being conceptually simple, has one significant drawback. And that is I have to do a lot of function calls. Okay, so you've probably, unless you've worked in high performance computing, you've probably never worried about this too much. But here's the truth, a function call takes quite a lot of time to be executed. Okay, so it takes a lot of cycles for a function to be executed. And since this is not your function, it's not your code, right? You're calling a function that is usually part of the kernel of the system, operating system's kernel. It's a driver that runs in kernel mode. It's a so-called kernel call, and that takes even longer to be executed. So it takes pretty long. So one thing that you want to do in generally any graphics API or any high performance settings, actually, try to minimize the number of calls. Try to literally minimize the number of function calls that start with GL. So that's pretty much it. So what's easier than that is, why can't we just throw all of the geometric information into one big array and say, here it is. And that's basically what vertex arrays are all about. It's an array of vertices. Well, I guess that's pretty much it. How does it look like? Again, it takes a lot of code around this, but kind of the key component is that we now throw our geometry into a single array here. Okay, that's our array, and I just used the constant array here. And then I get a reference to a part of my shader. So this is actually already considering programmable function pipeline, this code here. So I get a reference, which I call just here a vertex location. So I look in my shader in my program that runs on the graphics card. I look where it's positioned. I look this up, store this, and then I say, okay, well, now bind this pointer to position. This is what this vertex attribute pointer call does. Okay, it says, okay, please connect position in my shader code to this array here. Okay. And then if I want to, this is sort of a thing that I have to set up once. And then if I want to render this at some point, remember, OpenGL is a state machine. I say, well, now use this location. Go ahead, render. Okay. Render 1 triangle. What's this one? Sorry, render 2 triangles. It's a number of Let me think. No, it's one triangle. Yeah, it's one triangle. It's a number of primitives. So the third parameter is the number of primitives necessary to, or the number of inputs necessary to do the triangle. So 3 vertices makes one triangle, and then I'm done. So to be nice, I disable my array. Not that I have to do this. Another part of the code might enable another one, but I'll just disable this. Okay, so this greatly reduces the number of calls, right? It takes 2 or 3, depending if I do this disable call or not, to achieve a similar effect. And if it's 1,000,000 triangles, it's still 2. If it's 10 million triangles, 2, right? So that's the cool thing about this approach. The drawback, however, of this approach still is that this memory here at the top, right? This memory is my memory. I allocated that, right? I did a new call, or I did here an implicit new call. So I allocated this memory, and it's not on the graphics card. Okay, so every time this triangle is rendered, data has to be sent from the main memory to the graphics card. It's potentially cached somewhere along the way, but it still has to be sent, right? Maybe not from main memory, but from cache. But again, it has to be sent. Why does it have to be sent? Because I might change that memory location, and the system is not keeping track of that. So the next idea is, okay, let's allocate memory on the dedicated graphics card, dump the stuff there, and then just tell it to use that memory it already owns, so that we can avoid this transfer. We can reduce the number of calls, and we can avoid this transfer. So this is what a concept called buffer object is good for. So that's kind of Act 3. If I would, for completeness sake, I would have to go on at least to Act 4 or 5 to get you to the state of modern OpenGL. But I'll stop here and leave the rest for the exercises, okay? Just to give you an idea, and just, again, a glimpse of what is necessary. So basically, the code that you see here would come on top of the one you saw from Act 2. So I already have memory. I already have my array allocated and everything. So what you do next is, just conceptually, again, the details are important. I just want to get the concept across, is I now generate a reference on the graphics card. This is not memory, that's just a reference. And then I activate that reference. I say, okay, well, now apparently I want to write to something that is on the card. And then I do sort of like a mem copy. I do a copy of data from my vertex data pointer. And that would be something like this here, right? This would be something like this here. This would be my data that I have sitting around somewhere. I want to now copy that over onto the card, and then I give it a hint and say that's static. I'm not gonna copy that very often or never. So that tells the graphics card a little bit how to optimize access to that memory. If it knows, okay, this is never going to be touched, then it's probably going to cache it a little bit different. Okay, so now I've got the memory on the graphics card, and then I render this a little bit different. Again, details are important. There are a bunch of zeros here that basically tell the card to use the memory that is already on the board instead of copying it every time. Okay, so bottom line is we want to reduce the number of calls, and we do more and more processing before the actual frame. Okay, so all of this happens, this memory creation, this copying stuff, this happens ahead of the rendering, and then with high performance, I don't know, 500 times a second or so, we run through this code here. That's the basic idea. Just kind of a pointer that goes a little bit beyond what we want to talk about in this lecture. If you look at those low level APIs, such as Vulkan, which is kind of the successor to OpenGL. However, OpenGL is still around, and Vulkan isn't all that popular, as well as DirectX 12 or other low level APIs such as Apple's Metal API. They take this even further. This idea of reducing function calls. And the basic concept is that you're not only setting specific parts of your pipeline, like your geometry or whether you want to enable a certain feature or not, but you set all of the states at once. So you're in these low level APIs. I don't think they're called this way, but this is the best way to describe them. In these APIs, you end up creating a giant struct with all of the parameters in them that the card potentially has, and then you fiddle around with some of those, and then you always send this giant struct so that you override the entire state in one go, and that again reduces your number of function calls and makes things, depending on your application, faster. So if you have a lot of different states, it can really make a big difference. For some for actually a lot of application, it doesn't make a big difference, and that's why OpenGL and other APIs are still around and still very popular, because often it's additional workload for the programmer and it doesn't pay off that much, but it depends on your application. Okay, so that was pretty much how do we get the thing started? How do I tell the card, okay, this is the geometry, please do something. Now I need to tell it what should it do, right? How should it process the geometry and then scan, convert it, rasterize it, fragment process, and so on and so forth. Okay, so we need to talk about that one. What's the VPR? Oh, I saw a question. I just saw this now. What's the vertex pointer really doing? So let's just go back. If it's been a while here, you're probably referring to this one here. So this is, I mean, what is it doing? It's a pointer to memory, right? It's a variable. It's an array variable. And in C, an array is just a pointer to the first member of the array. So in that sense, C doesn't distinguish between arrays and pointers to memory. It's literally the same thing. So this array here is accessed through a pointer to its first element, and that's the vertex pointer. Okay, and this is the parameter here. So here at this point I say, okay, well, this vertex location should access data from that memory location here. So that's what the vertex pointer does. And then if I later on enable this vertex location, OpenGL looks up the information from the state that I set here, knowing that, okay, guy wants to render 3 vertices, meaning 1 triangle. Where should the data come from? It should come from this thing points to that thing is here. So that's the underlying idea. Okay. Yeah, geometry processing. Let's talk about geometry processing. At least a little bit. So we've got about 15 minutes left for today. One side note before I forget it. So the exercise and the lecture on Thursday. Is it Thursday? Yeah, I think it's Thursday, right? Are flipped. So if you look in LSF, it says lecture first and then exercise, but it's the other way around. It's first the exercise and then the lecture. All of my slides, everything is correct. It's just the order is just wrong in LSF. Okay, so we'll start with the exercise, and the lecture will be after a short break. So around 9:15, we'll start with the lecture. Okay, we'll start with the live stream. So just as a side note. Okay, geometry processing. How's that supposed to work? And again, a lot of words here. What do all of those mean? Okay, let's look at this. You can consider this whole processing as putting something into a pipe or a tube or whatever, and then doing some sort of processing with it, like, I don't know, bending it and then getting stuff out. So it's a pipeline, right? Stuff in, stuff out, pipe. And from a syntax point of view, you get the same stuff out as in. So you put vertices in and you get vertices out. Okay, so that's the first thing to know. So the syntax inside the vertex stream doesn't change. It processes vertices, produces vertices. Same is true for the fragment stream. It gets fragments as input, produces fragments as output. The change happens in the rasterizer. Okay, so but what does it do? What does it do? Well, it processes these vertices. And how does it process them? Okay, and that has something to do with this idea of a camera. What does the camera have to do with this whole thing? Well, if you want to render something, you need to define a camera or an eye point or a viewpoint or a viewer position. It's all the same thing, right? You want to view a scene. Unless you say, where am I looking at, and so on and so forth, you can't generate an image of an object, right? You have to know where the object is and where the viewer is or the camera is. Okay, now how can we describe such a camera? Okay, if we've got this old style camera here, how can we describe it? Well, let's first say, if I want to render the sports car here, and that's my model. Okay, this is my model that I want to render. What do I need to do? Well, first of all, I need to create the car. Okay, let's just say I did this. Done. But wait a second. When I create the car, I don't necessarily have its use in mind, right? Think about, let's stick with this car. Let's say we want to use a game where we drive the car through a city. Okay. What happens when I drive the car through a city? Well, I move it around. and I rotate it. I potentially rotate its wheels and they spin. So a lot of things happen to the geometry, but I don't do all of this stuff when I model the car, right? I just model it somehow, and then later on I'm gonna transform it somehow. Okay. So when I do my modeling, let's just talk about one simple thing. Where's the front wheel located? Oh, what type of question is that? Well, it's obviously here, right? Well, let's say back wheel. I can point to that one. Like it's here. But what I mean is, I mean, this is a mathematical thing, right? This model, if I break it down into triangle, then the triangles that make up the wheel, they have a coordinate. Now, where are these vertices of the triangles located? Well, for that to make any sense, we need to define where is the center, where's the origin. Now, if you were to design a car, where would you place the origin? Well, I guess you would probably place it in the center, right? And then, or at the front or something, right? Let's just stick with the center idea, right? And then the answer that I just asked is pretty simple. Well, if this is the center, then the vertices of the back wheel are, well, I guess 1.5 meters to the right. Right, and we can say to the right is positive, to the left is negative. Okay, let's just stick with simple notation here, right? So then this is clear. Okay, so this is about 1.5 meters, and then this is, I don't know, 20 centimeters up or whatever, right? And everything works. So just by deciding where to place the origin, right, we've, in a sense, solved this problem. Now, this is all good and well, and we call this the model space. So this is a space in which the car lives. Now, let's say I have another car in my city. Let's say I want to have this massive multiplayer online game with everyone driving cars around. How do I model that car? Well, let's say I want to do, I don't know, an old school pickup truck. And again, I would place the center of, or place the origin in the center. So it's pretty likely that it's the same place in that coordinate system where I put the wheels of my, I don't know, Ferrari or whatever that is. There's also the wheel of my pickup truck, and so on and so forth. So what you can see is the coordinates of everything, the wheel, hood, spoiler, whatever, in the game or the virtual environment are different from the ones that I used to design. So I have to do some sort of transformation to get from one thing to the other. No, I'm not talking about Z-buffer. Later on, Z-buffer, different thing. Okay, I'm just talking about transformations here. Okay. So when I model my car, I use one space, which is convenient to do the modeling, where I normally put the center of origin in the center of the car. And I do this for each and every car. Now, when I place the car in my city, I have to transform it. I mean, it's simple. I have to just move it around. I have to rotate it, and I potentially have to scale it. When I did the city in kilometers and I did my car in meters, I have to divide, which means scale all of its coordinate by 1,000. Okay, so that's what's called the model transformation. It's a transformation that I apply to my model to put it into the world. It's also sometimes called model to world transformation. Okay, that's transformation one that's going on. Okay. We'll later on see how things are going on. Well, orthographic, yet another thing. Z-buffer, other thing. One doesn't exclude the other. Never mind. Never mind orthographic projection here right now. So I just want to talk about this in general. Whether you use perspective or orthographic is just a detail. I'm not talking about the camera yet. Okay, so I'm just talking about the model. We place this somewhere. Good. Now we've got our object in the world, whereas the world, by the way, is made up of multiple objects. So now comes the camera into play. Okay, now we place the camera somewhere. What this means is, sure, we can take the camera, just like any object, and move it around, rotate it around, and then there's another rotation, which is sort of along the viewing direction. So we basically need, for the tripod, we need 3 pieces of information. Where's the tripod? Which direction does it point? That's what most people come up with. So what's the third piece of information? That's where it's up. Okay, if I place my tripod somewhere, let's say here, and then I decide, okay, I want to point in this direction, there's still a degree of freedom. That's a rotation around my viewing direction. So you need 3 pieces of information, an up vector, a position vector, and a direction vector. Okay, so that'll basically set up the tripod. So that's what I put here as viewing and position orientation of the camera. Now there's a very curious thing that you need to understand, and that is a camera transformation, this viewing position orientation, is not applied to the camera in OpenGL, but to the object. What does that mean? Oh, and why am I making such a fuss about it? The idea is the following. If you're looking at me, obviously, through the camera that's taking a picture of myself, okay? So if I move over, I move, okay? Now, say I want to move the camera around. So instead of moving the camera to, say, the left, I can also move to the right. You get the exact same image. It'd be indistinguishable from yourself. That's the whole theory of relativity stuff, right? And that's the idea in OpenGL. You never change the camera. As a matter of fact, the camera is fixed in OpenGL. You can't even change it. It's impossible. It's always in the origin, looking along the z direction. Okay, the negative z to be precise. So there's no way you can change the camera. But if you want to change the way, if you want to change the camera, what you do is you change the scene. You change everything else in an opposite way. Okay, shifting it to the left when you want to move the camera to the right, rotating it counterclockwise when you want to rotate the camera clockwise, so on and so forth. So the camera transformation is applied to the scene. Okay, very important thing here. Okay, so yeah, exactly. So theoretical warp drive, ship doesn't move. The world moves around it. So that's what's going on here. Okay, so and that's what we call the viewing transformation. Okay, because that's how we view the world. And the important thing is, again, the viewing transformation is applied to the scene as well. So we now have two transformations. Your car first undergoes this modeling transformation, scaling, rotating it, whatever. I'll talk about the transformation in the next stream. Next, it's rotated and translated so that it appears we moved the camera, right? And then there's more that we need to do. And this is now getting to the comment that we just have about orthographic and perspective and so on and so forth. So there's more, which I call lens here. So when I set the camera somewhere, or the tripod with the camera, pointing into a certain direction and make sure I know where up is so I can't rotate it anymore, there's more to this step because I have a lens system, right? I have a certain opening angle at which I view the scene. And that's what's called the projective transformation, okay, or projection. And that, again, is applied to the scene. Okay? Everything is applied to the scene. Okay? So now we've collected three transformations: model, view, and projection. As a matter of fact, the whole thing is called model view projection, spelled out as one word. Okay? And then ultimately, there's a third transformation that we apply that's called the viewport transformation. And that is basically just, well, how big is my image? How do I kind of chop things off? All right? And where do I place this ultimately on my monitor? Okay. But that's the entire set of transformations that we apply to the scene. It's all applied again to the scene. Okay. In OpenGL, this is expressed as a set of matrices. I'll motivate next stream that all these transformations can be, or almost all of them, except for this perspective division, can be represented as matrix multiplication. So we'll just end up doing a lot of linear algebra, very simple linear algebra. It's just literally matrix vector product. Okay, and you can set those matrices. For some weird historical reasons, the first two transformations in OpenGL get combined into one matrix that's called the model view matrix. When you later on write your own shader code, you can conveniently call one model and one view, and you can do it all yourself. But if you do fixed function pipeline, it's combined into one matrix. No big deal. That's just how it works. Then comes the projection matrix. Then comes a thing called perspective division. More on that later. And then finally, this viewport transformation, shifting this somewhere. Okay, so a bird's eye view here is we throw the vertices into the pipeline, and then we set those matrices. We set a set of matrices. So different matrices: a model view matrix, a projection matrix. The perspective division is done automatically, and a viewport transform. And then we get positions that are on screen. Okay, still continuous floating point positions, and those then get rasterized. Okay, so what the transformation part of the OpenGL pipeline does, it shifts, scales, shears, rotates things around so that I can look at them from the right direction. Okay, and that is actually the implementation, and also the use is actually very simple. It's a very simple concept. It's just, here comes my geometry. I mean, I made clear that can be a little bit mind-boggling, but this part is actually pretty simple. So you just say, this is my model view matrix, this is my projection matrix, and that's my viewport transform. It's 3 columns, more or less, if it wouldn't be a state machine. It's a little bit different, but that's the basic idea. Okay, and then we've got everything where it's supposed to be, and then it can be rasterized. And more on that later. Any questions for today? So let me stop here, continue on Thursday at 9. Any questions? So, it doesn't seem to be the case. What's clipping and frustum culling? More on that later. Yeah, that's basically throwing away information that is invisible because it's either so frustum culling. Just as a quick note, I mean, why not? Culling is throwing away stuff that is outside your frustum. If I go back to this image here, so this is it, like this frustum. This is what this viewing volume is called, frustum. Okay, this thing. It looks like a pyramid that's chopped off. Everything that's outside of that frustum, of the viewing volume, is invisible because it's behind you or to the sides where you can see it, and you want to remove that. That's what's called frustum culling. There's also other culling methods, and clipping. Clipping is the process of literally this cutting process. That's also part of frustum culling, potentially, right? So for instance, an object might be completely outside the frustum, then you can just cull it, remove it, but it might be partially inside, then you have to clip it, you have to cut it so that part is inside and the rest can be removed. Those are the 2 terms. No, I'm not using it for compression efficiency. I'm using it to cover fewer space because I think that part of my body isn't that really important. So that's the basic idea. In particular, if I make myself bigger, right, you can still see here, right? You can still see. The idea is just that you can see more of the slides because I think my hands are kind of useful to point to things. My face is sort of useful so you can see my gestures and everything. But the part here in between is pretty worthless for the communicational part. That's why I removed it by wearing a green shirt. Okay, so that's the underlying idea. It might be a little bit disturbing though to see a floating head. I agree, but I waited that the edit part of the slide that becomes visible is more important than my chest. That's the idea. Okay, anything else? Yeah. Okay, I guess we don't have any questions anymore. Then see you later, either on the next Advanced Imaging stream, the next Cyber stream, maybe grundlegende Programmiertechnik, or the late night codings, where we sometimes do graphic stuff as well, where we get our hands dirty with OpenGL and stuff like that. But yeah, until then, have a nice day, have a nice remaining week, stay healthy, and see you. Bye bye.